Hello, this is video number 1 on special relativity. In this series of videos, I'm going to introduce you the basic ideas of special relativity. And I'm going to go into some mathematical details and some physical interpretations of the theory itself. And of course, I'm going to tell you some paradoxes about special relativity and solve it. And those paradoxes are very useful in helping us to get a better understanding of the special relativity. Okay, those videos are about 30 episodes, and each video is about 10 minutes, maybe 20 minutes, up to the knowledge that I'm talking about. Okay, so the first time you heard about the special theory of relativity and look at the strange phenomena about time dilation, length contraction, and so forth, you may feel very bizarre. Those kinds of phenomena are weird. You may feel hard to understand. But don't be afraid of that, because actually special theory of relativity is a very interesting subject. And the more you get into it, you can feel the fascinating stuff about it. And actually, in some sense, it's quite an easy subject. Okay? So, you just have to have patience and is willing to think about those problems, scratch your heads, and spend a few days to think about them. I think you can get used to that, and you can handle it. Okay, so now let's get started. First, I'm gonna pose to you a problem. Suppose I have a car, okay, which is running at a speed μ0 relative to the ground. In the car, there is a man who is holding a gun, and he fired a bullet. Okay, and the bullet's speed is v prime relative to the car. So my question is, what's the speed of the bullet, which is seen by a man who is sitting still on the ground? I think this question is quite easy. The man on the ground will say the speed of the bullet is v, which is equals to the speed of the car plus the speed of the bullet with respect to the car. Okay, so this is actually Galileo's velocity addition, and this is quite easy, and because the first thing I want to mention is that the bullet has inertia, right? For if the man didn't fire a bullet and just carry a gun on the car, and the speed of the bullet in the gun is just v0. So if the man just drop the gun, let it go, without any external pushes, the gun will drop like a parabola. Okay, what I mean is that the bullet and the gun has inertia, which is because of what? Which is because of mass, right? The more massive the bullet is, the more inertia it has. Okay, So this makes the whole problem sensible, uh, because the bullet has inertia. So when you fire the bullet at a velocity v prime relative to the car, and the total speed of a bullet with respect to the gun is just the original speed v0 plus v prime. Okay, this is the first thing I want to mention. And the second thing is, let's draw a space-time diagram. Now I'm going to introduce you to the space-time diagram. Suppose I have a reference frame which is stick on the man, which is standing still on the ground, and let's name this reference frame K. Okay, and I have another reference frame which is sticking on a car. This blue frame, let's say it's called K prime. So what's the trajectory that the car move relative to the K frame? Okay, this is our K frame, and because this whole problem is one-dimensional, which means I want to choose the horizontal axis to be x-axis and forget about the y-axis and z-axis, because there's nothing about y-axis and z-axis. And now I'm going to say the horizontal axis is space, x-axis, and the vertical axis is time. So this red frame is a frame which is sticked or is pinned on the man or on the ground. And in this frame, what's the trajectory of the car? Is like this, right? The car moves at a speed of v0 relative to the ground. So we will see an inclined line. And here I want to mention that the trajectory of a car, this blue line, actually acts as double rows in this problem, which means that this is also the time axis of a car, right? Let's get back to see the man on the ground. The man on the ground, he has the time axis, or t. And what is his trajectory in space-time? Of course, he's not moving in space, but he's pushing forward in time. So this line actually is the trajectory of the man on the ground in a space-time diagram, right? So this axis actually has double rows. The first row he plays in is the time axis of the ground, or the man on the ground, and the second row he plays with is the trajectory or the world line. This is a professional word in special relativity. This is a world line of the man on the ground. And by the same argument, this blue axis is the time axis of the car, and also is the trajectory of the car, or the world line of the car in a space-time diagram. And this is called space-time diagram. Okay, so now let's come to the first point here. What if the bullet, what if I have an imaginary bullet which has no mass, which is a massless bullet, and the bullet is fired at a speed of v prime relative to the car? And the same question, what's the speed of bullet which is seen by the man on the ground? Notice that the bullet is massless, which means the bullet has no inertia. So the question actually is, the bullet's speed is v prime also seen by the man on the ground. So to get a better understanding of that is that there's now change your bullet to be a beam of light and